Okay, hello everyone. So Cem Curl here will present us the Cartan Hadamard Theorem today. Cem is a fourth-year student at Galatasaray University, and his mentor is Leyla Yardımcı, who is a PhD student at Wesleyan University. So now I'm leaving the stage to Cem.
Hello, everyone. It's a pleasure to be here. I'd like to thank the DIT team and keep it everyone, basically. I'd like to really quickly thank my mentor and really quickly plug the reference book because it's not at the end of the presentation. It's this book. Everything I'm about to talk about is in this book. It's Matrix Spaces of Non-Positive Curvature by Martin Abelson and Andre Haflicker. And the subject is entirely done, to my knowledge, but the techniques are being used to study other things at this point. Anyways, let's get started. Table of contents. First, I'll be giving a bit of preliminaries because this is metric geometry and we need some tools before we can understand the theorem itself. Then I'll be presenting the Cartan Hadamard Theorem. I'll give a road to the proof, and I'll explain the proof of the Cartan Hadamard Theorem. I will not be giving any proofs of the lemmas here. They're in the book. Also, they're really long, and require 4 chapters of material before. So that's why I'm not giving the proofs. Okay, we start with our first tool, one of my favorite tools, the humble geodesic. A geodesic is a path in the topological sense. So from a closed interval of R onto a topological space, specifically a metric space, it's a path, a continuous function. But it's not just that, it's also an isometry. What an isometry means is that for epsilon distance traveled between 2 points on the path, we have epsilon time that passes, if you will. Another way of seeing it is the inverse image of epsilon radius balls on the space around points of the path are taken to epsilon length intervals or open balls in the closed interval. It need not be unique or even exist in between points, but it's here. Basically, this is the definition. I have drawn these in the Nesin Mathematik Blackboard. They're going to be assisting the presentation. You can think of a geodesic as the shortest path between 2 points of a space. It's basically a generalization of that idea in standard Euclidean space. Reparameterizing geodesics to start from 0, 1 is a fairly standard process. You can do it for paths as well. For geodesics, it's kind of easy to. Anyways, here is a geodesic ray. A geodesic ray takes from R plus in the French division. That's 0 plus infinity on this interval. This should be open. Sorry about that. Its restriction to closed intervals are, of course, geodesics between 2 points. This is a geodesic ray. This is a local geodesic. Sorry, this is the ugliest picture here. They're differential geometries geodesics because they preserve the geometric structure of metric spaces that we care about locally. They can be characterized as being geodesics around a closed neighborhood of some point. Here, that's what I'm trying to depict, actually. It's a geodesic here when you restrict it to some closed. You can see it like that. We get to the interesting concept, the thing that we really care about. Geodesic spaces are spaces where each pair of points can be connected via a geodesic or multiple. A space is uniquely geodesic if there is only one, and this is going to be very important soon. And geodesics in a space, in a uniquely geodesic space, because we want the sequence of geodesics here. By the way, this notation I'm going to explain in a second. We want this this to be a sequence because if there are 2 geodesics between points, it's not a sequence. You get 2 outputs for matching number in the index. A space is uniquely geodesic if there is only one geodesic between 2 points, and geodesics are said to vary with their endpoints if given 2 convergent sequences. Given the singleton, this notation is the geodesics between xn and xy, xn and yn. This means this the geodesic between the two. It's a singleton. Converge uniformly to this singleton, which is the unique geodesic between x and y, the limits of these sequences. So basically that around sequences, things converge. We get to the length of paths. The length of a curve is the supreme of the sum over the start and end points of a path restricted to a directed partition of 0, 1. A curve is said rectifiable if its length is finite. The length is indeed reparameterization invariant, and it's given like this. I'm going to explain this. This is the set of directed partitions of 0, 1. That means partitions of 0, 1 where each piece is a closed interval, and the maximum of one is the minimum of the other, and you go stick them like this till you start with 0, so t0 is 0, and you end with 1, and it's just a bunch of closed intervals. This is the distance function, putting each piece of the partition, a particular partition, in direct 0, 1, like this, and it's the biggest of this. There's going to be a drawing. I'll explain it better there. The length metric of 2 points is given via the infimum of the length of paths connecting the 2 points. This metric plays an important role in our construction. Remember it. I denote it by a subscript L. This is the curve, the set of curves between 2 points. And given a curve, it's the smallest of the lengths of the curves. But this does not have to be a metric, by the way. It can be a pseudometric. If there are no rectifiable curves between 2 points, you have infinite distance by convention. So this is the visuals. Here I have a curve between the C0 and C1 points. Here I have given intervals, and I have considered these pieces as the distance function. I'm adding these up one by one by one by one by one by one, and you get a number at the end of this process. And you can do this for arbitrary splittings of the line, and you take the biggest of these to be your length. Now, convexity of space and functions. Right, the standard definition of convexity, does anybody remember it? No. Straight lines, with straight lines. Yeah, the standard definition of convexity is that given 2 points, the straight line connecting these two has to remain in the set. That's a convex set. That's a convex solve. It's not enough for us. We have to generalize it. So we generalize it in the following way. Given a geodesic space, a set is set convex if it contains the images of all geodesics connecting the points in it. And a function is set convex if its images in this sense. And this is a generalization of convexity that agrees with the usual definition of convexity given a non-vector space. And there are some theorems regarding Banach spaces that I'm not going to get into, and I don't remember particularly well either. Generally, the two definitions don't agree. A metric is set convex if the following is satisfied. Given any geodesic between 2 points, any two geodesics between 2 points. So perhaps drawing this might be more useful. Given 2 points of x and y and some number of geodesics. How many? There. Okay, I'll draw here. Given 2 points, x and y, and any number of geodesics between them, you want to be able to do the following. Sorry, I made a mistake. Given 2 points, x, y, and y1 and y2, and given geodesics from x to y1 and x to y2. You wish to be able to say the following, given C1 and C2, two geodesics, random geodesics to 2 points, starting at the same point, you wish to be able to bind. You wish to be able to put an upper bound on their distance at any point. T. You wish to put an linear upper bound by the distance between these 2 points in space, and that's what you want to do. And that's basically what I'm trying to say. This function should be bounding your distance function at any point at any point t, given any geodesic, starting from the same point and ending at any point in space. Length spaces. Length spaces are spaces that are given the length metric, the one we defined before. And the length metric is indeed a metric if there is at least one rectifier occur between 2 points. The balls of the length metric are contained in the balls of the metric we use to induce it. And if is a pattern X, if there is a pattern X with the length metric, it's going to remain a pattern with the usual metric. If C is rectifiable, it remains so. The length of a curve stays the same. And the length metric induced via length metric is itself. Also, hopefully no theorem, if a length space is complete and locally compact, and every closed and bounded subset is compact, and the space is geodesic. This is very powerful, but I'm not going to get into it. Ethyl maps and coverings. A map is an ethyl map if it's a local homomorphism with some conformity conditions on how things work. You can think of the standard definition or the standard example on S1 and R. We have the pullback length metric. Given a covering for P for a metric space X, one can associate a pullback length metric to the covering in the following way: DPL between 2 points in whatever are spaces, and is just going to be the infimum of the paths put through the cover. Put through the cover and measured in our space, in our metric space. Generalization of the exponential layer. Okay, consider the following space associated with pointed metric space. The space of local geodesics from our special points to a random point in the space, such that the domain is of the geodesics is going to be 0, 1. The constant map is a local geodesic. We're going to give this space the bar metric, which is the supremum of the distances between any 2 points, any 2 geodesics. Sorry. Yeah. Okay. Yeah. This is going to be the distance function put through T for the geodesics. So you can back to the picture. You can think of it as the distance here. This is going to be the biggest of these is going to be our distance in this space of paths, the space of geodesics. And we're going to define an exponential function in the following way: from the space of geodesics to the space taking a path with n. This is going to be very similar to the idea of an exponential map defined on the tangent space. If you know in the Riemannian geometry, on the tangent space, you can put a vector, you can pull it down onto the space, stick it like that. It's kind of like that. In fact, the road map I'm about to follow for Cartan Hadamard, which is this, is going to be very much analogous in the Riemannian geometry. That's with the Riemannian metric. Anyways, let X be a connected complete metric space. If the metric is locally convex, then it's universal cover under the induced length metric as a convex metric. This is going to be the theorem. Locally convex means there is a neighborhood around every point where the metric is convex. Proposition 1, given a length space and a term of P to that space from a host of space, the following holds. If the domain of P is induced by with the pullback length metric, then P becomes a local isometry. That means P preserves distances. The induced metric is a length metric and is the unique one to be both a length metric and satisfy Y. Proposition 2, let P be a map of length spaces, let domain P denote the domain and RP denote the range of P. the following list of properties, if the following list holds, then P is a covering. RP is connected, the range is connected. P is an eternal. The length of parts in DP are no bigger than the length of their there's a typo. Images under P. RP is locally uniquely geodesic, and geodesics in RP vary continuously with their endpoints, as defined previously. And the domain is complete, then P is a covering map. This is only true for maps between length spaces and nothing else. Lemma 1, take a locally complete and locally convex in the metric sense space. Let C be a local geodesic, pick epsilon small enough that the ball centered around a point of the geodesic, the closed ball of radius 2 epsilon, is convex and complete with the induced metric. And the following are true. Firstly, the distance function. There exists a unique geodesic given 2 points in epsilon balls of the start and end of geodesics. There exists a unique geodesic such that the distance, there exists a unique local geodesic, sorry, local, such that the distance function is a convex function for that geodesic and R path. Given the length function, we have the following always holding. This is a bound for the length of the specific unique geodesic. But perhaps an image will be better to explain what's happening. So we pick a point around the ball at the start, we pick a point around the end of the start, and this is our local geodesic. At any point, there is an epsilon ball of radius, if there's a ball of radius 2 epsilon, and we have one geodesic satisfying the conditions given by the lemma. Lemma 2, suppose X is a metric space that is locally complete and locally convex. I know very horrible conditions. Then the following note, the space defined before the geodesic space is contractible. In particular, it's simply connected. The exponential is a local isometry, and there is a unique geodesic joining the special constant map. So this one. Going to take any two. There is a unique geodesic in this space joining this constant map to any point, so to any path on that space. Third lemma, let X be a metric space X0 some point. If X is complete and the metric is locally convex, then the path space is complete. And X be simply connected, a simply connected length space with a metric that is complete and locally convex. Suppose for any pair of points there is a unique local geodesic C joining the pair. If these two geodesics vary continuously with their endpoints, then the following holds. Geodesic, it was local, it's become a geodesic, and the metric on X is convex. You see where this is going. Corollary, let X be a connected metric space on X0 point. If the metric on X is complete and locally convex, then the following holds. The exponential is a universal cover. Universal cover means the domain of the exponential for space X is going to be connected, locally pathwise connected, and semi-locally simply connected. That's what that means. And each pair of points in X tilde is joined by a unique geodesic. So X tilde is a unique geodesic space. Then back to Cartan Hadamard. We can now prove Cartan Hadamard because all of those very, very, very specific lemmas are going to come in and come together right now. So supposing the assumptions made in Cartan Hadamard that our space X is connected and complete and locally convex in the metric sense, we have the following. The exponential at any point is a covering map. It is a local isometry, and there is a unique pullback length metric making the space such by proposition 1. The length metric associated with this is the same as the pullback length metric of with the usual metric of this. Remember, it's the supremum of distances. It's the same as the pullback length metric from X. So we have a very interesting situation. There is a unique local geodesic between points, or in the length space here, because length spaces and the usual metric act very, very nice together. And by lemma 1, there is a local geodesic. The local geodesics vary continuously with their endpoints. We are done because lemma 4 said this. If there is a local geodesic such that they vary continuously with their endpoints, and C is geodesic and the metric on X is convex, and Cartan Hadamard said that X be connected complete metric space. If the metric is locally convex, then its universal cover under the new strength metric has a convex metric. We are done. Presentation is done, so at least the part I prepared, but I have some bonus time, so it's bonus presentation time over there. I can use this, right? I'm going to show you some of the stuff we skipped over. So this is not the full Cartan Hadamard theorem. There is a second part. There's a second part, and to be exact, the second part is related to Alexandrov patchwork, which we're not going to get very much into. Second part says if X is of curvature less than or equal to K, where K is smaller than 0, then the length space, as shown previously, is a cat K space. Now, allow me to explain what that is and what we're going to try to do with the convering if I 5 more minutes. Okay, very good, very good. A cat K space is basically this. It's a space where geodesic triangles. Oh. Bayağı koşturdun ya iki tarafa da anlatmak için. It's a space where geodesic triangles between 3 points are no fatter than a certain fatness. If you get what I mean. You know, triangles can be a bit fat, a bit thin, depending on where you draw the geodesic triangles. If you draw them on a sphere, they're a bit fat. On a hyperbola cone, they're a bit thin. A cat K space is one where triangles are no thinner than a certain given thinness. These spaces are very important. For example, off the top of my head, a Banach space that is also a cat K space ends up being divergent, if I'm not wrong, just by nature of the fact that there is curvature. That's, for example, some of the applications. I think I am done. Thank you. And plugging the book one last time, this book is good. The subject is apparently very well researched, according to my mentor, and still being researched in the US. Thank you for listening.